today I don't think we have enough time, but we consider such a case when we use D1-alkene boron compound. If we use diisopropoxy boron compound, we can overcome such a difficulty. For example, in this type of cross-coupling reaction with this compound or this compound, under these conditions, in this case, if we use G1-alkene dicyanide boron compound, we can obtain this compound in higher enzymatic purity, but yield was only 49, less than 50%. However, when we use G1-alkene dialkoxy boron compound, such as diisopropoxy boron compound, we can obtain the expected product in high purity and high product in 87%. Consequently, we found we can synthesize all kinds of conjugated alkadiene by using such a bind-bind cross-coupling reaction. Thereafter, many chemists apply such a reaction for the synthesis of their target product conjugated alkadiene. I show you one of such examples. Next slide, please. This is the synthesis of this compound reported by Coleman's group. Coleman group tried the cross-coupling reaction of this alkene bromide and this alkene boric acid. Under this condition, they found they can obtain this expected conjugated alkadiene in 85% yield. Followed by this reaction, they obtain this target product. Not only of this example, we had many of reports concerning such a cross-coupling reaction of alkene boron compound to the conjugated alkadiene. But today I don't think enough time, so I cannot tell you much more. But next slide, please. I'd like to show you one wonderful example. That is the synthesis palytoxin reported by Professor Kishi in Harvard University. They reported the total synthesis of palytoxin. Palytoxin is a so big national product, toxic national product. They reported the total synthesis of palytoxin. That was I think 90, after 1990, I can't remember exact time, but in this year, 1989, they reported such a complex application of our bind cross-coupling reaction to synthesize complicated conjugated alkali system. That was reported in 1989. I think 4 and 5 years before they reported this paper, I was invited to give a lecture at Harvard University. At that time, Professor Kishi told me they are planning to synthesize this palytoxin using our cross-coupling reaction. According to his explanation, they are planning to synthesize two necessary components, this red component and this black component, independently. Finally, they cross such a component at this position using our cross-coupling reaction. So finally, they succeeded to synthesize such a palytoxin itself. Next slide, please. Here, in this slide, I show you a little bit about the reaction mechanism of alkene boron compound with alkene halide. As I told you in introduction, initially we considered such a coupling reaction may proceed through tetra, this type of compound, tetracovalent this compound, with alkene bromide in the presence of aluminum tetrate to give expected conjugated alkadiene. In order to make sure such a speculation is correct or not, we actually tried this reaction, and we found actually we can obtain this conjugated alkadiene, but yield was only 9%. So in order to obtain some evidence of this mechanism, we carried out some reaction indicated under this line. First, we tried the reaction of this compound with the tetratetraphenyl phosphine by Friedland procedure. Then we can obtain this compound. Fortunately, we can obtain this compound as pure solid. Next, we try this compound with sodium methoxide by Oatscard procedure. Then we can obtain this compound. Again, we can obtain this compound as pure solid derivative. So next we try the reaction of this compound with alkynyl boron compound. In this case, without any base, at room temperature. Even after 17 hours, we never obtained any expected cross-coupled product. However, in this reaction, when we added base sodium methoxide at room temperature, only after 2 hours, we found we can obtain this cross-coupled product in 89% of product. Next, we try the same type of reaction using this compound instead of that. This compound and this compound with the alkynyl boron compound. In this case, without any base at room temperature, only after 15 minutes, we found we can obtain this compound in 66%. When we try this reaction for 1 hour, we can obtain this product almost completely. Consequently, we consider in this type of coupling reaction, this type of alkynyl palladium alkoxide, this compound should be necessarily intermediate. Consequently, next slide please. We consider such our reaction, binding cross-coupling reaction may proceed through reaction pathway indicated in this slide. First of all, alkynyl halide, the oxidative addition of alkynyl halide to palladium 0, then we can obtain this intermediate. This intermediate reacts with base to give alkynyl palladium alkoxide. This compound is necessary intermediate. This one reacts with alkynyl boron derivative to give dialkynyl palladium intermediate. Finally, the reductive elimination of this compound may occur to give expected cross-coupled. In this case, we can obtain conjugated alkyne, and also we generate the palladium 0 compound. By this the reaction mechanism, this reaction proceeds to give expected product. In the case of organoboron compound, as I told you, we need this step. On the other hand, other cross-coupling reaction using other organometallic compound, we don't need any such a base. That is very big difference in the case of our cross-coupling reaction using organoboron compound and other cross-coupling reaction using other organometallic compound. Recently, two different groups, one in Spain, one in Brazil, they reported their interesting paper, and they suppose this coupling reaction proceeds just as we indicated in this slide. According to their paper, this alkynyl boron compound reacts with the base to give this alkynyl alkoxy boron derivative. This compound leading reacts with this to give this. Anyway, this reaction is considered to proceed through reaction pathway indicated in this step by 4-step reaction. Next slide, please. Here, in this slide, I show you another cross-coupling reaction of alkynyl boron compound with the many different kinds of organic halide. First, here, I show you the reaction with halobenzene. Iodobenzene, brombenzene give us expected this product in almost quantitatively. But chlorobenzene only give this compound, only 3%. So when you try the same reaction of chlorobrombenzene, in this case, we can obtain this compound in almost quantitatively. That means coupling only occurs at this bromine position, not occurs at this chlorine position. And also we found all the substituted phenyl halide similarly react with alkynyl boron compound to give expected product without any difficulty. Not only the reaction of aromatic halide, next slide please, but also heteroaromatic halide similarly react with alkynyl boron compound to give expected coupling product. And also we found allylic chloride similarly react with the alkynyl boron compound to give expected product. I told you previously, aromatic chloride is very enough, but allylic chloride is very effective. And also we found benyl halide, one one alkyne similarly react with alkene one compound to give expected product in I product E. Next slide, please. I told you previously, excuse me. I'm sorry. I told you previously, many of alkene boron compounds react with the number of organic halides in the presence of palladium 0 and the base to give expected cross-coupled this type of compound in high product field very selectively. So next we try same reaction by using the saturated alkene boron compound instead of that. Of course, as you know, this compound is very easily prepared by hydrogenation of terminal olefin. So we tried this reaction, but unfortunately, we couldn't find any expected product, cross-coupled product. For us, we never obtained when we use desaturated alkene boron compound. Next slide, please. Here, I told you, if such a reaction may proceed through reaction pathway indicated cross-coupling reaction between the binding boron compound and the binding halide, as I showed you previous slide. If such a reaction proceeds to give this compound. Finally, reductive elimination occurs to give expected this compound. Similarly, like binding conjugated alkyl TCC. However, in this case, we have to consider another possibility. That is, if the dehydroparonation occurred from this, we may obtain another type of product indicated in parentheses. Maybe in this case, another type of reaction may occur. Therefore, we never obtained the expected product. But fortunately, that is 1984, at that time, Dr. Hayashi, he came to this university as a professor. So some of people here know Professor Hayashi, Tamio Hayashi. Professor Hayashi's group, they discovered very nice catalysis in this reductive elimination stage. That is, next slide please. That is this compound, palladium dichloride, DPPF. DPPF means different phosphoroferrocent. So when we use this Hayashi catalyst, the cross-coupling reaction between the iodobenzene and the B-oxyl 9-butane in the presence of sodium methoxide in KHF at refractive temperature, we found we can obtain this expected oxybenzene in almost quantitative. However, in this reaction, when we use other palladium catalysts such as tetrahydrophosphine palladium, we never obtain this expected product. So big difference. And also we found this alpha bromonaphthalene react with this alkyl boron compound under similar condition to give expected product. Not only the reaction of aromatic halide, we found alkenic halide like this react with the desaturated alkyl boron compound under similar condition to give expected cross-coupled product. Therefore, thereafter, many chemists all over the world applied such a coupling reaction using alkyl boron compound. For example, next slide please.